Hi everybody. So here we've got a past exam question on modeling with differential equations. We're told that the watering of crops on a farm is thought to affect the concentration of nitrates in a nearby river. In a study, the concentration of nitrates in the river is measured at a point downstream from a farm, and the concentration of nitrates is modeled by this second-order differential equation, where Y is the concentration in milligrams per liter and T is the number of hours after the crops were watered. We need to begin by finding a general solution for the concentration of nitrates after time T hours. So we'll need to use the auxiliary equation to find a complementary function, and then we'll need to find a suitable particular integral to deal with this term. Do you want to give this question a go yourself? You can pause the video, and when you come back, you can check your work with mine. Okay, so welcome back if you want to go. So we need to find the auxiliary equation. You can see that the A term is 1, the B term is 2, and the C term is also 1. So we need to solve m squared plus 2m plus 1 equals 0. And this is m plus 1 squared. So therefore the solution is m equals negative 1. And because we've got a single distinct root, we can use the complementary function, where we'll have a plus bt multiplied by e to the negative t. And this negative comes from this negative 1. So we've substituted this into here. And this is our complementary function. And I'm going to expand out these brackets. So we've got the complementary function. Now we need to find a suitable particular integral to deal with this term. Now ordinarily, because we've got e to the negative t plus 1, but this won't work, because lambda e to the negative t is similar to what we have in our complementary function. So what we would do is we would multiply this term by t. But now we have the same problem, because this term is now similar to the b term. So we need to multiply it by t again. So our particular integral becomes lambda t squared e to the negative t plus mu. And now we have this, we need to work out dy by dt, so we can substitute it into here, and the second derivative, so we can substitute that into there. And you can see we've got two functions of t multiplied by each other. So we're going to need to use the product rule to differentiate this. If we let u equal the lambda t squared term, then u prime will be 2 lambda t. And we'll let v equal e to the negative t, so v prime will be negative e to the negative t. And now we can use these to find dy by dt. So dy by dt will be the u term multiplied by the dv term plus the v term multiplied by du. Now I can tidy this up. We'll write this term first, followed by this one, so we don't start with a negative. So dy by dt will be 2 lambda t e to the negative t minus lambda t squared e to the negative t. And now to work out the second derivative, it's much easier to factor out this e to the negative t and the lambda. So we get lambda e to the negative t multiplied by the 2t minus the t squared. Now we can differentiate this again using a product rule. This time we'll let the u term equal lambda e to the negative t, and v will be 2t minus t squared. So dv, or v prime, will be 2 minus 2t. And now we can use these to work out the second derivative. So we'll have a u term multiplied by the dv term plus the v term multiplied by the du term. And then we can tidy all of this up. Then we'll factor out the lambda e to the negative t from both terms. So we'll get the 2 minus 2t minus the 2t plus the t squared. And then we can collect the t terms together. And this will give us our second derivative. Now if we go back to our original equation, we've found this term and we've found dy by dt from our particular integral. We need to substitute each of them back into here, and then we can equate the terms with the right-hand side. So I've substituted these in. Now we need to expand out these brackets. So I expanded out these two. Then I'll expand out these. And we've got our y term and the right-hand side. Now I'm just going to expand out this 2 with these terms here. And now at this point, we can look at collecting the like terms. If we look at the t squared terms, we've got 1 here, negative 2 here, and a positive 1 there. So the t squared terms will cancel to make 0. If we look at the t terms, we've got negative 4 here, positive 4 here. Then these will cancel. So we're left with 2 lambda e to the negative t and the positive mu. And this will equal the right-hand side, e to the negative t plus 1. So therefore, the 2 lambda must equal 1. So lambda will equal 1/2. And the mu is a constant that must equal 1. Okay? So now we've got the values for lambda and mu, we can substitute them back into the particular integral. So our particular integral will be 1/2 of t squared e to the negative t plus 1. So now if we combine this with our complementary function, we can put them together to give us our general solution. So we've got our complementary function here and our particular solution. And this is part A completed. So if we go back to the question, now for part B, we're told initially the concentration of nitrates was measured as 1 milligram per litre, and according to the model, the concentration was increasing at a rate of 9 milligrams per litre. So we can see that when t equals 0, because initially y must equal 1, and then when t equals 0, it's increasing at a rate of 9, so dy by dt must equal 9. And these are our initial conditions. Now we can use these to work out the particular solution by finding A and B. So if you want to give this bit a go yourself, again, you can pause the video and come back when you're ready. Okay, so I'll come back. So if t equals 0 and y equals 1, we can substitute them into our general solution. So 1 will be A e to the 0 plus b times t e to the 0 plus 1/2 of 0 squared e to the 0 plus 1. We know the b term will go and this term will go. So we've got 1 will equal a plus 1. Therefore, a must equal 0. And now to find the value of b, we need to work out dy by dt. So we need to differentiate y. If I just substitute in first that a is 0, then this term will go. So dy by dt, we'll differentiate this using the product rule. So we'll have bt multiplied by negative e to the negative t plus the b e to the negative t. And then we need to differentiate this again using the product rule. So we'll have 1/2 of t squared minus e to the negative t plus, when we differentiate this, we just get t e to the negative t and this constant will go. And we know that at t equals 0, dy by dt equals 9. So we'll have 9 b lots of 0 minus e to the 0 plus b e to the 0 and 1/2 of 0 squared minus e to the 0 plus 0e to the 0. We can see that this term will go, this term will go, and this will go. So b will equal 9. And now we can write our particular solution. We'll substitute the 9 into here. And that's part B. If we go back to the question, for part C, hence determine the maximum concentration of nitrates after the crops were watered. So we need to work out dy by dt and then set that equal to 0. That will give us the value of t, which we can then substitute back in to our particular solution to give us our maximum. So do you want to work out dy by dt from this yourself? Again, you can pause the video and come back when you're ready. Okay, so welcome back. So dy by dt, if we differentiate this using a product rule, we'll have 9t minus e to the minus t plus 9 e to the negative t plus 1/2 of t squared minus e to the negative t plus the t term e to the negative t, and then this constant of 1 will just go. So when dy by dt equals 0, we can factor out the e to the negative t. We'll get the negative 9t from here plus 9 minus 1/2 of t squared plus this t here. So we can tidy this up. We'll have e to the negative t of 9, negative 9t plus a 1t, negative 8t minus 1/2 of t squared. Now we know that e to the negative t can never equal 0. So our solution must come from this quadratic. And we can solve this on our calculators. We get t will equal a negative, which we can discount, and a positive solution when t is 1.05 approximately seconds. So we'll substitute this value of t back into it, and that will give us our maximum concentration. So y will equal 9 lots of 1.05 e to the negative 1.05 plus 1/2 1.05 squared e to the negative 1.05 plus a 1. When we work all of this out, we get approximately 4.5 milligrams per liter. So that's our maximum concentration here. For part C, the concentration of nitrates is believed to return to its initial condition 8 hours after the crops are watered. State with justification whether this is supported by the model. So if we substitute in t equals 8, then if it does return back to its initial condition, we should get y to be approximately 1. If we do, this would be supported by the model. So do you want to substitute in t equals 8 and see what you get? You can pause the video and come back when you're ready. Okay, so welcome back. So if t equals 8, then we'll have y. We'll substitute the 8 into our particular solution for t. So we'll get 9 lots of 8 e to the negative 8 plus 1/2 of 8 squared e to the negative 8 plus the 1. When you work all of this out, we get y to be approximately 1.03. And you can see this is approximately 1. So we can say that the model supports the suggestion that y returns to its original value. Okay, well, thank you very much for watching. I hope you found that useful. If you want more practice on modeling with differential equations, you can download the lessons and the worksheets from my website, mrmathematics.com. I'll leave the link in the description below.